Okay, hello.
Right. Next, we have Pavel Panteleev giving us a talk. I actually don't have his title, but based on David's talk, I assume he's going to tell us about product expansion, something related.
Yeah. So I'm going to discuss this product expansion, but before that, so I assume that David already gave a very good setup, yes, for this problem. So, so as you can see, this idea of product expansion, so it appeared as a way to ensure that you have some good local properties in these cubical complexes. Yes, we have some cubical complex, and we want to have some, yes? Okay. Okay, maybe I will start just from this. Okay, so how we can see what is the tensor product code? So there are several ways how we can view tensor product code. So first of all, the most natural way is just a set of matrices, yes, with some local codes assigned to every column and row. So we have some column code A, yes, and we have some row code B. And this is what is usually called tensor product code. And but another way to view it, which is due to Tanner, if you remember in his paper, when he introduced Tanner codes, he also introduced, showed that these tensor product codes are a special case of his construction. And what he showed that we can consider, so suppose this code, let us assume that this code has the parameters n by n, yes, just for simplicity. So we can consider bipartite graph with two parts. And so and we can consider complete bipartite graph. Yes, so we're going to have edge for every pair of vertices. And when we fix a vertex here, so we fix, for example, column. Yes, this corresponds to column. And this corresponds to rows. And when we fix column and row, we fix some element of this matrix. And what Tanner showed that you can view this tensor product code as a special case of his construction, Tanner codes. Yes, when we have local code A everywhere here, yes, and when we have local code B everywhere here. So this is just a special case, and so we can write that this is the same as Tanner code with this graph. Let me just maybe denote it's like two bipartite graph with n vertices, with n vertices in each part, of course. And we have local codes, yes, A and B. So we have local codes A and B. And if you you can see that from the previous talk, yes, this is one of the instances of a sheaf code, yes? So it's a sheaf defined on this graph, on this bipartite graph. And so what is the natural generalization of this construction? This is, of course, yes, we can consider tensor product of several codes. So we have d-dimensional object here. And we can also view it as a sheaf code. And in this case, it would be bipartite complete simplicial complex. And so let me show it's just maybe on 3, so it's easier to see. Yes, we have 3 dimensions now, and we fix, so we have some fix some vertices, and its hyper edges give us, so its hyper edges of the largest dimension give us exactly this 3-dimensional object. Yes, so we have 3 dimensions, so we fixed here, here, and here, and we get one element. So we can view this tensor product code as a code defined, so either on the three-dimensional grid or d-dimensional grid in the general case, yes, or either as a sheaf code. And what are the local codes of these sheaf codes? Okay, so we can also view it, even this in more general settings. Yes, we can also view it a special case of a Tanner construction. So what are the local codes? So in this, for example, in this three-dimensional case, yes, we assign local codes in the Tanner construction to the edges. Yes, so we have, so to each edge we assign, and if edge, for example, goes, so we assign to the every edge, and edge is a object of dimension, maximum dimension -1, and this means that so for all edges that goes from here to here, for example, we can assign. So let us assume here we have code A2 and A3, and to each this edge we assign the code to this edge. A2, yes, for this code A3, for example, and here A1. So on each edge, we assign a code word, yes? And as was shown in the previous talk, so you can, and we assign this local code, but where we place our bits. Yes, our bits are placed on these hyper edges, so on these triangles. And we have the number of these triangles. You can see that we have the number of these triangles, the length of the code. Yes, it's equal n to the power of d. Is it clear? Any questions? Okay. And each local code can be in this three-dimensional picture, can be represented as some kind of local local code that checks the bits in some line. Yes, and we have axis parallel lines only. Yes, so we consider only axis parallel lines. Okay, this is a geometrical picture, and actually the reason why we called it product expansion, because it's so if we consider tensor product code as a sheaf code on the simplicial complex, yes, on the general case it is this simplicial complex, then we can define different. So we can define cohomology of this simplicial complex, and from the previous talk you saw how you can do this. And in our case, we are mostly interested in the last layer of this cohomology. And so this last layer, this is exactly the layer that I showed to you here. So we have, for example, in three-dimensional case, edges, and the last layer, triangles. Yes, but in more general case, we have like d-1 dimensional simplexes where we put bits, and d-2 dimensional hyper edges where we put these local checks. And now we, in a natural way, how we define this Coboundary map. So we define it in the following way. So our chains, and this was the question, yes? So I'm just trying to answer this question. So what we have? We have the following chain. Let us denote sheaf by F. And so this sheaf, it like contains different layers. So as I said, we have d-2 dimensional objects, which in this case corresponds to edges, yes? And we have d-1 dimensional objects, which in this case corresponds to triangles. And we let us do much simple. So so if we apply now if we apply this Coboundary map, yes, we need to obtain out of the edge, yes, we need to obtain a sum of let us assume that of course this space consists of linear combinations of, let us denote it sigma, where sigma is this edges. And when we apply this, we just got the following formula. So we apply in the standard way. So each edge is connected to some number of triangles, yes? And we can see that all these triangles, tau, that contains this sigma, which is an edge. And we do the restriction maps, yes? So we restrict ourselves to the neighborhood of this edge. And by neighborhood, I always mean when I talk about neighborhood, I mean only the hyper edges of the highest dimension. Yes, so this has all the hyper edges of the highest dimension that are okay. Let me put it explicitly. So we restrict these code words to this set. So each edge is connected to some number of triangles, yes? And to the edge, we assign some code word, and we restrict it. And here we get these triangles. So it's pretty easy. So it's not so hard, but for proofs, it is much easier to represent it in a little bit different way. So, and I will show you in a minute how we represent it in our papers. And for this reason, we need some additional object that is usually called as a dual product code, or quite recently it is also usually called check product code. What that is? This is the following thing. So, so if we can see the tensor product of several codes, how we can represent them? We can define the code CI, which is and in the if position, we will have CI, and in all other positions, we will have just no restrictions. So it just means that we consider all these d-dimensional matrices where we have restriction only in is dimension. And how we can define this code? So we can define it as an intersection. So we just put all the restrictions, yes? But you can also consider this not the intersection of these codes, but also some of these codes. And so we introduce some little bit silly notation that we often use. And this is what is usually what we call dual product code or check product code. And the reason for this, why it is called check product code, because the parity check matrix for this code is tensor product of check matrices for the component codes. And actually, so you can show, this is quite easy, and this is also one of the ways how you can define this thing, is that it is equal to So it's just a dual of the tensor product of dual codes. So it's like dual object. And by the way, in the sheaf theory point of view, this is what is called co-sheaf. And this is a co-sheaf code. I will not talk about this because I don't have enough time, but so the proper name for this would be co-sheaf. Okay, and is this definition clear? Okay, now what we should consider? We should consider this chain complex, and we can define, of course, we can define in the standard way the Coboundary expansion for this chain complex. But this way, so we have some coefficients which are code words, and we count every non-zero code word as one. So this is important for this definition. So here, everywhere by the norm, I mean the norm that is related to this complex X, where we count the number of non-zero pieces. Yes, so for this, yes, for this chain, this is equal to the number of non-zero elements here. And we can define a standard way Coboundary expansion, but it turns out that, and this idea was first presented in a little bit different way in the paper by Livier and Zimor and on quantum Tanner codes. And you can represent it, this Coboundary expansion in a very elementary and beautiful way. So it's using this idea of dual tensor code, so we can say the following thing, that so let us consider, so what is this space? This space, so let us consider the image of this. So the image of this delta is just exactly for this complex that we consider here is just exactly the sum of these codes. Is it clear that this is the case? Because so we choose code word and just project it. When we project it, it means that we just have a code word that contains everywhere zero just in one line, so we have a code word. And all their images is just the sum of these things. So this is exactly the image of this. And so we can also define this Coboundary expansion as a property that for every, let us write it in this way. So if we, for every image y, which is of course from this tensor product, from this sum of the codes, we can find lines, so we can find elements. So let me put it this way, so we can find elements. Okay, let me just put it this way. So we can represent this y. So we can find its pre-image in this norm. So the idea is the following. So if we take the image, we can find the pre-image, which weight is bounded by the weight of this image. And in fact, so I also should say that this complex, it contains, so its homologies are zero. It is quite easy to check. And for this reason, this Coboundary expansion can be represented in this much simpler way. So we find for each image, yes, we find pre-image, which is a sum. What is pre-image? This is this cochain. And what is this cochain? This chain is a linear combinations of, for example, edges, yes, and each edge, it contains like one line. So this means that if we have some code word, y, we can construct it as a sum of lines, and the number of lines is, let me put it this way. So for y exists x such that so if we have image, yes, which is just a code word of this sum, yes, we can construct a number of lines. So X is a collection of lines, and what is a, so here, as I said, so we use this special norm, and what this special norm counts. So on the level of bits, on the last layer, yes, we count the number of bits, number of non-zero bits. But what we count on the previous layer? So on the previous layer, so we have lines, and we count the number of non-zero lines. So what this definition says that for every x, for every x, every y. For every y, we can find its pre-image, which is not large. And in the simplest case, in the two-dimensional case, yes, it's so you have some non-zero code word, yes, and you find some lines such that you add them and you get this code word. And so the definition says that if your weight of your code word is small, then you can obtain it as a sum of small number of lines. This is a general idea, of course. Okay, so let us move. How much time do I have? Okay. Okay. And okay. Okay. And so what we prove? We prove that this value, which we can denote AD, by the way, if you apply it just to a code, then this is exactly the minimum distance. That is why, so sometimes we refer to it as a high-dimensional analog of the minimum distance. And so what is the main result? Okay. So the main result is the following, that if we fix some rates, then for a couple of codes that we choose uniformly at random from the collection of all possible tuples of codes with the parameters n, ri, n over the field 2 to the t, we have that the distance, or not the distance, so let me just denote it in this way. So this expansion of these codes is okay, so it grows linearly. So this is kind of so analog of good codes. So the expansion is good. And this also happens with high probability. So it happens with probability at least 1 minus n d 2 to the power n d minus t plus 1. So you can see that if you use sufficiently large fields, so you can make, because this n is constant in all our constructions, yes? So the size of the local codes is constant. It means that we can choose non-binary codes of sufficiently large field. And if we do this, you can see that we have this with high probability. And so let me just very briefly say you the proof idea. Very, very briefly. So it involves the following component, which I think is important. So we say that subset S is epsilon closed if for every line in any direction, if this line intersects a lot with this subset, yes? And subset, by subset, I mean just support, some possible support of some code word, yes? And so here I am considering this code, yes? Dual tensor code. And this means that L is an S. So this is a special combinatorial property, yes, of a subset of the n-dimensional grid. If we have a line that intersects a lot, this line should be in this set, not inclusion, so it's this sign, yes? This line is subset of this S. And so we call this epsilon closed, and we can also, of course, define epsilon closure as a minimal subset that is epsilon closed and contains S. And another important property, so we say that S is extendable if we have X, which is code word of these two tensor product code, which have support in S, then we can always cover it with the sum of lines. Where this XL are from, each XL is from the what we call a line code. So the code that lives on the line L, yes? In each line, we have a code in each direction. So it, so in this simple picture, yes, so it means that, so we have S, we call S extendable, yes, if it can be, so every code word with support in S, inside S, can be obtained as a sum of lines. So this is a simple definition. What, and the reason, so there are some reasons why we call it extendable, because this is connected. So we can show that if we go to the dual code, yes, which is a tensor product code, then in this case, this exactly corresponds to extendability of local sections to global sections in a sheaf. And yeah?
Do these lines have to be in S?
Support of X, no, they should not. No, it's not necessary. So it's so we can just recover it. Oh, no, sorry. Yes, they should. Let me add this. And and now what we do in our proof. So we first we observe that this property of good Coboundary expansion is just equivalent to the property that there exists epsilon, which is theta n, such that all epsilon closed sets are extendable. Yes, so in order to ensure good Coboundary expansion, we need just to look at this combinatorial property. So all sufficiently large, so epsilon closed sets should be extendable. And so this is fact one. Maybe I can remove this. And the fact two, that if we have a collection of codes that are good LTCs, and I assume that everyone here knows what are good LTCs, like Dinur's C3 LTCs. Then the Coboundary expansion of the tensor product of these ones are good. And the last step we show that there exists in some kind of universally, we call it maximally extendable codes. Maximally extendable codes over sufficiently large alphabet. Over Q, sufficiently large. And what are these maximally extendable? It means that we can see the all possible codes, tensor product codes, with the parameters, with some fixed parameters. So let us fix the rates and consider the codes with these parameters, all possible codes. And we call it, and we also, for example, choose this field size. And we say that the code is maximally extendable if whenever S is extendable in one of the codes from this family, it is extendable in this code. So it means that it extends as many S as possible. So in sheaf theoretical point of view, it means that this code as a sheaf, yes, has this maximal extendability property that local sections are extended to global sections. So this is, and now we just need to connect all this. And in order to prove this, that such codes exist, we use techniques that were previously used in the very similar concept called maximally erasable, maximally erasable, yes, recoverable, maximally recoverable, yes, maximally recoverable tensor product codes. And this is exactly the very similar idea, but do I have any time or just? Okay. So let me just show the difference. So is it clear how we using these three facts so we can derive what we need? Yes. So here we have some universal codes that has as many extendable sets as possible. Next, we show that there are examples of codes that have good Coboundary expansion. And by the way, you can ask me why I just don't use these codes to prove my theorem. Does anyone see why I do this? I think no, because because I forgot to say about that. So the real thing, what we need to show that we have both of these are good. If I just use LTCs, yeah, I can just go in one direction, but I need it in both directions. And which means, and this result, since it holds with high probability, so it holds also with for the dual of the codes. Yes, so it simultaneously holds for the tensor product of codes and tensor product of their duals. So and so here I use these good LTCs as examples. Yes, that shows that we have codes that have sufficiently many extendable sets. Yes, that are epsilon closed. And so using this fact, yes, so I can derive that. So this maximally extendable codes, it inherits the property of this universal maximally extendable code. But let me just briefly say what is the difference between maximally recoverable tensor product codes and maximally extendable, because I think it's worth mentioning. So the main difference between them is the following. So what is maximally recoverable code? We consider all possible codes with these parameters, with some fixed rates and some fixed lengths. And we say that a code is maximally recoverable if if it's universal in the sense of information set. So it means that for every information set S, and information set of a code is just, so I assume everyone knows, yes, so information set is just bit positions that we can fix and recover all the code word. And the code is, the tensor product code from this family is called maximally recoverable if whenever we have an information set in some code from this family, we also have information set in this code. So it means that it has as many information set as possible. And those codes are very important for practical applications because you can recover information if you lost in your tensor product code all the data outside of S. You can recover this by looking at S. So in a sense, they are generalization of what is called MDS code. So maximally distant separable. You can see that in the case of in one dimension, this is exactly maximally distant separable. But what are these maximally recoverable codes? In maximally recoverable codes, we are interested, so when we consider S, we consider only, so we define the following thing, that is, we call a local section. So this is all the bit strings that we put here on this subset S that satisfy only the local checks, only the checks that corresponds to lines that are inside of S. So CS is a local code or local section of this sheaf in the sheaf theoretic terms. So it's, I think the definition is clear, yes? Okay, and we, of course, we can also consider the projection of, so C, here by C, I mean tensor product, yes? And we can also consider the projection of this tensor product code to this set S of all the code words. And when we have this property of extendability, so we say that S is extendable if, so in general, of course, we have this, yes? Because every, no, not this, sorry. This, yes? So we, if we just restrict our code word, our global code word to this subset, then it should satisfy all the local checks. But we say that S is extendable when we have here the equal sign. And so we ask about a similar property, yes, and you can see that this is, so we require more, because if S is information set, then information set cannot contain any lines. And so we ask that this property holds for all information set, but we also ask it for more sets. So in this sense, so it's a little bit stronger property. And currently, so the open problem is whether these two things are the same or maybe, so my conjecture also is that code is maximally extendable and the product code. If both TE and are maximally recoverable. Okay, so this is an open problem.
Thanks, Pavel.
Thank you.
A bit over time, so maybe we'll take questions in the coffee break, and we'll convene back at 11:15. Maybe take a little extra 5 minutes.